So far in the last some classes, we have studied about flip-flops. So in the basic, we have four types of flip-flops: D, SR flip-flop, JK flip-flop, and T flip-flop. The flip-flop in general is a single bit storage device which stores a single bit either in the form of zeros and ones. We have studied about different race around condition in the SR that has not allowed conditions. So when we are talking about the arithmetic logical manipulations, so we need shift registers to store temporary data. So shift registers are the combination of flip-flops arranged in such a way that we can use flip-flops to store data or to move data to a desired direction. So let's start with the basics of the shift registers. And the first, let us have the definitions of what the shift register is. A shift register is a digital circuit with two basic functions, and these are data storage and data movement. So in general, we can say when we have to store the data in our computer, then we use registers to store data, and as well as registers are used to move data. Now our shift register provides the data movement function as well as it shifts its output once every clock cycle. So when we talk about the clock cycle, we have in this way we say the active clock. The clock may be a level triggered when we are talking about the latches. So there are two levels, logic 0 and logic 1. Any one of the logic may be active level, and we have two transitions, 0 to 1, that is positive edge triggering, and 1 to 0, that is the negative edge triggering. So we have four different ways for the triggering of the flip-flop. So we can say when there is an active triggering, it will shift its data with 1 bit. We'll discuss in detail when we are going to discuss in with some examples. So in general, we can say that shift register provides the data movement function, and movement is 1 bit per clock cycle. A shift register is a group of flip-flops set up in a linear fashion with their inputs and outputs connected together in such a way that the data is shifted from one device to another when the circuit is active. So when we are talking about the circuit is active means we are getting a triggering pulse. So triggering pulse may be logic 1, logic 0, positive edge triggering or negative edge triggering, as we have discussed when we are discussing the flip-flops and the latches. Now, the applications of the flip-flop are concerned means it is used converting between serial data and the parallel data. So whenever whenever you are fetching your data from a serial port USB universal synchronous bus, so data is stored in a parallel manner in your computer, and when we are connecting the external device with the computer with the help of a serial with the help of a USB, then we say that it is connecting from parallel to the serial. Means in USB the data is serially out. Again, when you connect a USB port and the data in the USB is stored into the computer, then it is serial to parallel conversion. So we can say the shift registers are used for serial to parallel conversion and parallel to serial conversion, as we have discussed in case of multiplexers and the demultiplexers. Another application is temporary storage in a microprocessor, that is scratch pad memory, some arithmetic operations like multiply and divide. When you are multiplying two numbers, then every time you are multiplying the number with the next bit or next digit, you have to shift the data into the left side by one bit or one digit, as you are using in the paper and pen. Every time you multiply a number, you have to shift with one digit, and that is here in the computer we use shift register for that purpose. Similarly, in case of the division, when we are dividing a number with another number, you for each next division you have to shift to the right side then again this shifting is done with the help of the shift register, because it is very much easy to do in the on the paper with the help of paper and pen. You can just simply shift with the one bit, but in case of the computer, when you are doing the process digitally, you need shift registers for this purpose of the multiplication and division, where you need to shift a digit. Yeah, also it is used for the communication as UART, universal asynchronous register transceiver. Some counter applications like ring counter, Johnson counters, linear feedback shift register, LFSR counters, and we are going to discuss in detail all these. Sometimes to provide a time delay, we use shift registers. We store the data, and when we require the data to be fetched, we give an active clock, then the data will be stored. And there are many more such applications when we are going to discuss in the next some coming slides and some coming lectures. Now the characteristics defined for the shift register, when we talk about the type of shift register, the first is serial in, serial out, that is SISO. Serial in, parallel out, SIPO. Parallel in, serial out, PISO. Parallel in, parallel out, PIPO, and the universal shift register. So these are the type how the data is in and how the data is out. So in means data is for the first register SISO, data is serially in and serially out, means one bit is entered at a time and one bit will be out at the time. Serial in, parallel out, data will be input serially and the data will be fetched parallelly. Here the third is an PISO, data is in parallelly and the out serially. When we talk about serially, that means one bit will be fetched or one bit will be entered with a single clock cycle. And the parallel in, parallel out, PIPO, data is parallelly in and the parallelly out. And we have universal shift register which can perform all the operations above in a single shift register. Now the direction of the flow of data, we have left shift, we have right shift, we can rotate in a circle, that is either right rotate or the left rotate, and we can use in the bidirectional shift register which can move in both sides, left shift and the right shift. So these are the type of shift registers, and there are 5 types of shift register, and we have 4 types of directions in which a data can move into a shift register. So here we can see the block diagram of the shift register. Here I have put it as n bit shift register. Here data is input serially and it is output is serially, then it is SISO. These are the shift pulse, that is clock pulse. We have a preset asynchronous input. We have clear and asynchronous input, because every time you have to store data or the read data, either you have to preset the flip-flop, that is all digits in the output of the flip-flop is 1, or you have to clear the data, that means all output of the flip-flop is 0. So we have 2 asynchronous inputs as preset and clear. Shift pulse is your clock pulse, that is enable. So serial in, serial out. If we take serial in, parallel out, parallel in, serial out, and parallel in, parallel out. So these are the 4 types of shift register: SISO, SIPO, PISO, and PIPO shift registers. So this is a general block diagram. When we are in the next slides, we are going to discuss one by one all type of the shift registers. Now for the data movement, the bits in a shift register can move in any of the following manners. So here graphically I have tried to explain how data move in a shift register. So these are the floor blocks I have seen 1, 2, 3, 4. These are the 4 flip-flops. How these are arranged, we are going to discuss in the next some coming slides. So here data is in from the leftmost side, and bit by bit it is moving, and data is out, that is serial in, shift right, serial out, shift register. So shift is we are shifting in the right direction. So data is input as serially and data is output as serially. So here serial in, serial out, but the direction is shift left. Data is input from the right hand side and it is out from the left hand side. So again, I have put it 4 blocks. These 4 blocks are nothing but these are 4 flip-flops. So I may say that this is a 4-bit shift register. Means it can store 4 bits of data at a moment. Here I am parallelly in, 4 bits are parallelly directly into the flip-flops, and data is output is as parallelly, serially. It is now data is input as serially and the output is parallel. So I say serial in, parallel out, 4-bit shift register. Parallel in, parallel out, 4 bits are parallelly directly input with a single clock cycle, and these are fetched as parallelly with a single clock cycle. So it is a parallel in, parallel shift out shift register. All flip-flops have their advantages and disadvantages. Some is the cost, some is the speed. So whenever we are using a such type of shift register, we have a trade-off between speed and the cost. When we need a high speed, then we have to pay more. It is a rotate, right rotate, data is rotating in the circle, means here data is in, then it is rotating, and with the help of the preset and clear, we can set our data or the output of the flip-flop at any moment. It is rotate left, again we can move our data in the left hand direction. So with the help of the preset and the clear, we can store data, whatever should be the output of the flip-flop, that can be decided. So these are the data movements in the flip-flop. First is serial in, serial out, shift right. Serial in, serial out, shift left. Here it is. Parallel in, serial out. Parallel in, parallel out. Sorry, parallel serial in, parallel out. Parallel in, parallel out. Rotate right. Rotate left. So these are the data movement in the shift register. The block diagram of the shift register with various inputs and the output options. So here is first, in the last slide, we have just shown the input and the output. So here will be serial in, serial out. We have a preset control, we have a clear control, and we have a shift pulse. Shift pulse is nothing but your clock. Serial in, parallel out. Here we have a clear control and a shift pulse. Parallel in, serial out. We have preset, shift pulse, and the clear control. Parallel in, parallel out. We have preset, shift, and control. And when we are using it as a universal shift register, it will have all options: serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. And the synchronous, asynchronous inputs are preset control and the clear control, and we have a shift pulse, that is a clock. Now let us discuss first the serial in, serial out shift register. So here is the block diagram. Here it is the input, which is serially in. Here will be the output, that is serial out. One is the preset control, one is the clear control. So depending upon the value, what we want to initially store in the flip-flop, if we want to store that output of the all flip-flop should be 1, then what we do, we will activate preset. If we want that the output of the all flip-flop should be 0, then we will activate clear control, and the shift pulse is used just like a clock pulse. So the data bits come in one at a time and leave one at a time. Means at a moment, a single bit will be input to the register and the single bit will be output from the register. So as clear from the name, serially in and serially out. So here is the block diagram, general representation. One bit is entered into the flip-flop and one bit is out from the flip-flop. One flip-flop for each bit to be handled. Suppose we are using a 4-bit shift register, then we have to use 4 flip-flops. And in your current scenario, whatever processor you are using, either in your mobile or in your laptop or computer, you are using 60-bit of the processor, 64-bit of the processor. That means for a shift register, which is capable to handle a 64-bit microprocessor, you need a 64 flip-flops in that particular register so that it can parallelly store 64 bits. So here we all the theory will be discussed on the 4-bit shift 4-bit connections. In the same manner, you can extend your circuit of the shift register up to 64-bit. So in general, for a single bit storage, we need a single flip flop, and when we are using n bit storage, then we have to use n flip flops. Movement can be left or right, but is usually only in a single direction in a given register. So movement depends upon the connection, how you are doing your connections. But for a serial in, serial out, either it will be a shift left or a shift right shift register. The asynchronous preset and clear inputs are used to set initial values. If you want that the register value should be 0, 0, 0, 0, then it will be a clear. If you want to 1, 1, 1, 1, then you have to activate preset. So here we go. That is the basic serial in, serial out shift register. We have used 4D flip-flop, data flip-flop. These are the 4D flip-flops. So I have written A, flip-flop B, flip-flop C, flip-flop D. Clock is common to all flip-flops. So when we are discussing flip-flops, we have put it clock here. So for the simplicity, I have just put it in the lower line of the rectangle. So here it is clock. Whenever clock is active, all flip-flop will behave like whatever is the input to the flip-flop. And the property of the D flip-flop is that whatever is the input, whenever clock is active, that will be reflected at the output. If the clock is 0, then the output of the flip-flop will be stored. Whatever is the previous value, that will be stored in the D flip-flop. So it will be convenient when we are using, when we have to design a register, then it is desired that every time you use a D flip-flop, because when I was discussing the flip-flops, I have told you that it is a data flip-flop. Means whatever is the data, whenever clock is active, the data will be at the output of the flip-flop. That means it simply stores the data. So it is convenient to design a shift register with the help of the D flip-flops. So data is serially here, data is in. Whenever clock is active, this data will be at the output of the flip-flop, and that is input to the next flip-flop. Whenever next clock is active, this data is reflected here. Whenever next clock is active, this data will be reflected here, and wherever next clock is active, this data will be reflected here. So it will be convenient when we are going to discuss is with the help of an example. The simplest shift register is one that uses only flip-flops. So we are not using any other combinational logic or combinational gate. The output of a given flip-flop is connected to the D input of the flip-flop at its right. Each clock pulse shifts the content of the shift register 1 bit position to the right hand side, as we have seen the connections in the previous slide. The serial input SI determines what goes into the leftmost flip-flop during the shift. The serial out SO is taken from the output of the rightmost flip-flop. So here we can see the connections. Serial in D, Q is the output here. Q is the output of the A flip-flop. This output of the A flip-flop is the input to the B flip-flop. And the output of B flip-flop is input to the C flip-flop. And output of the C flip-flop is the input to the D flip-flop. Here it is the output. Here is the common clock. So the output of the given flip-flop is connected to the D. Here is the input. The output here is here. So output of the first flip-flop is connected to the D of the next flip-flop. That is the simplest connection, and this is the simplest shift register, serial in, serial out. So I have written here 4-bit shift register because I am using 4 flip-flops. So each flip-flop will store a single bit. A simple way of looking a serial shifting operation with a focus on the data bit is illustrated at the right as we are going. So suppose a 4-bit data word 1011 is to be shifted into a 4-bit shift register. So we have a 4-bit shift register and we have to store 1011. So let us see how it is done. As we have discussed, one shift per clock pulse is required. Means at a single clock, a 1 bit is entered in the flip-flop, and data is shown entering at the left-hand side. Suppose initially with the clock 1, whatever is done, the first one. So here is 1011. Whenever first clock is active, 1 will be entered to the first flip-flop. With the second clock pulse, next one will be entered. So the output of the flip-flop will be 1, 1. And suppose we have cleared the data, initial it was 0, 0, 0, 0. So with the first clock, 1 is entered to the A flip-flop. Now A is transferred here to the B flip-flop and the next one is entered to the A. With the third clock, A is transferred here, this 1 is transferred here and 0 is entered. With the fourth clock, this one comes here, this one comes here, 0 comes here, and next one is entered into the flip-flop. So we can see that we require 4 clock pulse to enter a 4-bit of data into a 4-bit shift register. So clearly we can see that for a single clock pulse, a single bit is entered into the flip-flop. With the arrow, I have shown the direction of the data flow. Now suppose I have given the 5th clock pulse. So what will happen? The first bit will be out. This first bit will be out at the 5th clock pulse. At the 6th, next bit, 7th, next bit, 8th, next bit, and the data will flip-flop will be clear. So in the next some coming slides, we are going to how to load and how to unload the data from a serial in, serial out shift register. So if anybody have any doubt, then you can write me in the chat box, and I'll explain your doubts. But as this is the pretty much simple and the basic shift register serial in, serial out. And now the more coming shift register will be much tricky, and there will be a complex circuitry to design the shift registers. Now let us take an example. The diagram at the right side shows a 4-bit shift register sequence is to the input is 1010 is being loaded into the 4-bit serial in, serial out shift register. So now we are loading 1010 into a 4-bit shift register. Let us see how it happens. Initially, I have cleared the flip-flop. The output of the all flip-flop, you can directly see 0, 0, 0, 0. You can see here 0, 0, 0, 0. Means I have cleared the all flip-flops with the asynchronous input. So I have written here register initially clear. The output of all flip-flop will be 0. I have used 0, 1, 2, 3, 4 flip-flops. It is a 4-bit shift register and it will store 4-bit of data. Now what happens when the first clock comes? So 0 will be transferred into the flip-flop. So this 0 will be here, this 0 will be here, this 0 will be here, and the input to the flip-flop is 0. First clock pulse. Second clock pulse, what happens? This 0 is out, 0 comes here, 0 comes here, this 0 comes here, and the next bit is 1, because 0 with the first clock and 1 with the next clock. Next clock cycle, now what will happen? Third bit is 0. Then again, here 0 comes here, this 0 is out. Here comes 0, here comes 1, and the next bit is 0 at the output, the 0, 1, 0. With the next bit is 1. So what happened? This 0 will be out, 0 is here, this 1 is, 0 is here, this 1 is here, 0 is here, and the next bit is 1. So 0, 1, 0, 0. So you can see directly that 4 clock pulses are required to load a 4-bit of data into a 4-bit shift register, which is serial in, serial out. So that we can directly see that it is consuming 4 bits, 4 clock cycles. That means the speed of this particular serial in, serial out shift register will be slow. So each bit moves one position to the right each times the clock's leading edge, and 4 clock pulses loads the register. Now suppose we have to unload this particular sequence, that is we have to fetch the data and store to the another location. So 1010 it is unloaded from the 4-bit serial in serial out shift register. In the same manner, suppose initial value is 1010, what we have loaded in the last slide. So what happens when the first clock comes and I am entering a data 0, I am clearing one by one the flip-flop. So whenever first clock comes, 0 is entered, this first bit is out. The first bit out is 0. With the second clock pulse, this 1 is out and 2 zeros are entered in the flip-flop because I am continuously entering 0. With the next clock pulse, this 0 will be out and 1 will be here. And with the next clock pulse, this final data final bit 1 will be out and the data register will be cleared. So you can clearly see that it requires 4 clock cycle to unload the data. So 4 cycle to load, 4 cycle to unload, means it is requiring 8 clock pulse to load and unload the data. That means if we are using n bit shift register, or simply you can see if it is a 64 bit processor, then the register will be of 64 bit. Now to load the shift register it requires 64 clock cycles, and to unload the register it will require 64 cycles. That means for loading and unloading it requires 128 clock cycles. That means your the working of this particular shift register is pretty much slow. So each bit moves one position to the right each time the clock leading edge. 4 clock pulses unloads the register. Now, as far as the applications are concerned, SISO shift registers are often used for the data communication, such as RS-232, what you use in your computer to connect your monitor with the CPU. So in general, this is the diagram. Serial in data, output of the first register is the input to the next. Next means the output of one register is the input to the next register. Clock is common, and the last most flip-flop will be the output of the final shift register. Another applications are modern transmissions and receptions, Ethernet links, SONET, and many more. These are the applications where we need not worry about the speed, but we require a simple basic connections. So where here we use serial in, serial out shift registers. Now the next is a serial in parallel conversion, means input is serial, output is parallel. We often need to convert from serial to parallel conversion. For an example, after receiving a serial transmission, we need to store it parallelly or fetch it parallelly, as in case of the USB drive. The diagram illustrates a 4-bit serial in parallel out shift register. Here it is the block diagram. Data is input serially, data is fetched parallelly. We have a shift pulse and we have a clear pulse. So here is the simple block diagram, 4-bit output, single bit input, and data flow from the left hand side to the right hand side. So here is the connection. We have given a clear to all the flip-flops so that initial data may be 0. Clock is common to all flip-flops and normal connections are there. But what we have done, instead of taking serially output, we have taken output parallelly from the each flip-flop. We would use a serial in parallel out shift register of arbitrary length n to convert an n bit word from serial to parallel conversion. It requires n clock pulse to load and 1 clock pulse to unload. So it is very simple, as we have seen whether in the case of serial in, serial out. So it requires for n bit shift register, it requires n bit to load the data, and after n bit with the single 1 clock pulse, we can unload the data. So here is the normal connections. Connections are same, but the only difference is that output is fetched from each flip-flop parallel. So here is the connection. Simply with the 4 clock pulses as input, with the we can load the data A, B, C, D, and at the same moment, this data is at the input of each flip flop. This is to read and this is to load. So what happens after 4 clock cycles? Suppose the data was 1010. After 4 clock cycle, data will be at the output of the each flip flop A, B, C, D. And whenever first one clock is given to the upper shift register, it will load the data parallelly to the output of A, B, C, D. So these two shift registers are used to convert serial data to the parallel data. The upper shift register would grab the data once it was shifted into the lower register. Whenever lower register is fully loaded with a single clock cycle, the data is fetched out from the upper shift register. So lower shift register requires 4 clock cycle and 1 clock cycle is required to load the data into the output. So it requires n plus 1 clock cycle, and again we can say in seed, or as in case of the serial in serial out, the parallel in serial out is comparatively faster as compared to the serial in serial out. But you can see that for this for the purpose of converting serial to parallel conversion, we require two 4-bit shift registers. That means when we there is a trade-off, speed is faster, but you require more number of flip-flops. That means cost will be high. So let us stop our discussion here. In the next class, we are going to discuss some more type of shift registers.